Okay, in this video, I'm going to practice proof writing. So I'm going to work on specific techniques. When you see these problems, how can you kind of think about them and how can you convert like ideas into nice proofs? And I'm just going to go through, I'm going to do this one about unique limits, this one about adding. This one was done in the forum. A student did this one in the forum, so I'm not going to do that one. There was a nice proof there. And then I'll do these two as well. And I'll put timestamps hopefully here where you can skip to the one that you want to see if you only want to see one. Okay, let's do it. So a convergent sequence has a unique limit. So this is, I guess, problem 22, exercise 22A. And again, we're in the setting of a normed metric space. So we want to say a convergent sequence has a unique limit. And the first thing you got to do is you got to convert this into a mathematical statement. I'm going to convert it like this. I'm going to say if xn is a sequence, so xn is my sequence. If xn is a sequence, let's call the vector space V, and limit as n goes to infinity of xn equals, let's call it A, and the limit equals B. So if you have a sequence and it has a limit which is A and it has a limit which is B, then A equals B. Then A equals B. So that's the way I converted it. So unique means there is only one. And here what I'm saying is if you have, whatever it is, it has to be the same thing. Okay, there we go. So every single proof in this course and just sort of in math in general, you can think of it as a path connecting what you have to what you want. And what I want is very clear. I want to show that A equals B. What do I have? I have that the limit is A and the limit is B. N goes to infinity of the xn equals A, and the limit as n goes to infinity of the xn equals B. And to think of the sort of path between these, how am I going to possibly prove that A equals B? Well, what do I actually know? I know these limits, but I could further unpack the limits and say that what that is more precisely. So I could say it with epsilon delta, but just in the ideas phase, I think it is more helpful. I think about it like this: xn gets close to A, let's say arbitrarily close to A, and I like the word eventually. So the picture in my head is like, here is the point A, and here is the sequence of the xn's, and it's floating around here. It's like x1, x2, x3. Okay, and they're in some abstract space, but I can still sort of imagine them as points, and I can think of the norm as the distance. So we have the sequence, and eventually it gets like really close to A. So here's like x 1,000, and like they get really, really close to A. And I know that also for B. Okay, so here is B. Let's do B in a different color, B. And the xn's, they're getting really close to A, and they're getting really close to B. They're getting arbitrarily close. So xn's get arbitrarily close to B, right? That is what the limits mean. And I like to think of it in time, so I sort of like imagine that we're getting like one point in the sequence out per second. So x1 comes out at time 1, x2 comes out at time 2, and so on. And as we wait long enough, eventually they're really close to A and really close to B. So why should it be that A equals B? Well, I guess the reason is how could xn get close to A and close to B if they were different? And at this point, you have a choice. To prove A equals B, you could think of what I just said is, should we do it by contradiction? So this is sort of ideas. By contradiction, what if A is not equal to B? What if A is not equal to B? So this is kind of going with the idea. I'm like, how could it possibly get close to A and B if they're different, right? So what if they're different? You could also do it directly. So maybe you have a different idea. This would be a different idea, which is, what's another way to say that A equals B? Well, if A equals B, then actually for all epsilon greater than 0, the distance between A and B is less than epsilon. And that's because the distance between A and B has to be 0 if they're the same, right? That's the same exact thing as A equals B. So this is another way you could sort of bring in these epsilons, is to do this kind of, we'll prove that for any epsilon greater than 0. And you sort of, as you're thinking about the problem, you have to pick a path and sort of try it. In this particular problem, both paths will lead you to the right answer, but I like the A is not equal to B. What if A is not equal to B? If A is not equal to B, then there is some epsilon, so that the norm of A minus B is bigger than epsilon, right? It's the opposite of the thing I just said. If they're not the same, there's some distance sort of between them. And I can add this to my picture. So it sort of looks like that and like that, right? There's some epsilon that lives around over here. In particular, you don't need this for the proof, but you could say, in our case, epsilon equals the norm of a minus b over 2. That works. It's like any number that's smaller than the norm. And this is very nice because how could it possibly be that the xn's are getting close to both the a and the b? And now I have an epsilon. And in fact, let me call it an epsilon naught, because I like to use epsilon naught when it's some particular epsilon rather than an arbitrary epsilon. And so we have this epsilon naught that kind of separates the a and the b. And once the a and the b are separated, then we can use that xn is within epsilon naught of a and xn is within epsilon naught of b. And then this will be a contradiction. So xn eventually within epsilon naught of a and xn eventually within epsilon naught of b. And if I combine these things together, I can get a contradiction. So these are my ideas. I haven't written any proof yet. This is just the ideas phase. And now I'm going to combine it to get a nice proof. And I'm going to do all the nice proof writing things. So proof. Okay, so what is this proof? Well, it's a proof by contradiction. Every proof by contradiction starts with the words suppose by contradiction. Suppose by contradiction a is not equal to b. Okay, when a is not equal to b, then there is some epsilon naught so that the norm of a minus b is greater than epsilon naught. Okay, this is a perfectly good way to do it. You could also say, this specific epsilon naught would work. A minus b is bigger than epsilon naught. Their distance is bigger than epsilon naught. And now I want to do this thing. Xn is within epsilon naught of a, and xn is eventually within epsilon naught of b. But I'm going to write it in the specific math way. Actually, you could write it both ways. This is something I like to do sometimes. You write it the sort of intuitive way, and then you also write it the math way. And then, the intuitive way is really just to tee up the reader to say, look, I'm about to give you the math definition. This is what it means, but here it is precisely. So that can be nicer too. Some people make the mistake of only writing it the intuitive way and not the precise way. Some people write the mistake of only writing it the precise way and not the intuitive way. And then if they make like a small mistake, you can't understand what's going on. So sometimes it can be nice to write both. Let's write both. So let me say xn is eventually, so let's do a since the limit as n goes to infinity equals a, since the limit as n goes to infinity of xn equals a, xn gets within epsilon naught of a eventually. And precisely, I can say there exists n, let's call it na, because it's the n that goes with the a's, the na such that xn minus x, not minus x, minus a is less than epsilon naught for all n greater than na. This is another common mistake I've seen, is that people write statements like xn minus a less than epsilon naught, and they don't say for which n they're talking about. So always make sure every symbol that you're talking about should be sort of qualified. Like epsilon naught, we know what is epsilon naught, we know it from up here. What is n? We know it from n bigger than na. This kind of stuff. Every symbol should be defended, sort of. Okay. Okay. Similarly, since the limit as n goes to infinity of xn equals b, and then I could repeat everything exactly the same. That would be perfectly nice. But I think the reader at this point in the proof of reading my proof, they have an idea of what's going on. So I could probably just skip to there exists nb such that xn minus b is less than epsilon naught for all n greater than nb. Okay, so I got my na, I got my nb, I've got the specific epsilon naught where these things are a minus b is bigger than epsilon naught. And now I'm going to put it together. And the thing I'm going to have to use to separate these two points is the triangle inequality. So the triangle inequality really is this idea of like you can't like be close to two things at the same time because the triangle inequality would be violated. And so specifically, I'm going to try to set it up as a chain of inequalities that ends with a minus b is less than epsilon. So I'm going to start with now. I'm going to say now consider, that tells the reader, look, there's going to be a sequence of sort of equations coming up, and I want to do a minus b, and I want to end it with less than epsilon naught, right? Because epsilon naught was specifically chosen, so it was bigger than that, and that'll be my contradiction. So I'm going to do this sequence of inequalities. I'm going to do the triangle inequality. The triangle inequality, I'm going to use it in this form that, let's say, star plus heart is always less than star plus heart, right? So whenever you have a sum of two things, you can split it apart, and you get a less than sign. And so that's going to gel into my less than signs over here to get to epsilon naught. So this is the way I'm thinking about setting it up. I'm getting ready to use the triangle inequality. Of course, you could conceptualize it a bunch of different ways, but this is the way I find helpful to think about these things. What do I want? What do I have? What am I going to use? That's how I'm thinking about it. Okay, let's do it. So a minus b, what do I actually have? I have xn minus a and xn minus b. So I better make these xn's appear. And this is one of those situations where you can add and subtract. So the a minus b is the same as a minus xn plus xn minus b. Okay, now it's time for the triangle inequality. So I can say by triangle inequality. Here's a quick way to write triangle inequality. Triangle inic. This is a minus xn plus xn minus b. And this is the same thing as xn minus a, because you multiply by minus 1 in a norm, and it's all good. And then that is supposed to be less than epsilon. I could give these names. I could say this thing, I could call this star A, and I could call this thing star B. Let's do it in all one color. So I'm not cheating by using multiple colors to add clarity. Okay, star A, and this is star B. And then I could say by star A, this thing is less than epsilon naught, and this thing is less than epsilon naught. Oh my goodness, I wanted a minus b is less than epsilon naught, but I got a minus b is less than epsilon naught plus epsilon naught. This is an extremely common thing that will happen when you're writing proofs, is you will sort of have mostly the right idea, but you have missed some detail. Occasionally, you need to sort of rewrite everything. Like you need to add something. You're like, oh wait, I need to fix something. In this particular case, it is quite easy. All I got to do is I got to make my stars to be epsilon naught over 2 and epsilon naught over 2. And then over here, they will be epsilon naught over 2 and epsilon naught over 2. And that will be equal to epsilon naught. Okay, I'll say it. And I forgot to say it by star B as well. Okay, so that's epsilon naught. So that's a perfectly nice proof. Let me erase this little hint that I gave myself for triangle inequality. That's just how I think about triangle inequality. Okay, and then I can read it over one more time. So we're doing suppose by contradiction. Very nice. We found this epsilon naught that separates A and B. I chose xn to be with an epsilon naught of A, xn to be with an epsilon naught of B, and then I have this nice sequence of inequalities, which is leading us to a contradiction. The thing I haven't done at the end, I've said I have to tell the reader, hey, this is a contradiction of this thing over here. So you could give this, again, you could give this a name. You could call this dagger. That's a good one. Okay. And then I could say, this contradicts the choice of epsilon naught in dagger. Okay. And then, we did a proof by contradiction. Sometimes people write a little arrow like that to mean, hey, the proof by contradiction is over. Okay, that's very nice. Proof by contradiction of why limits are unique in normed vector spaces, starting from what we have, what we want, the ideas, and then turning that into a nice proof, making sure to write everything nicely, good mixture of words that explain things and equations where they're appropriate. Okay, let's do problem C, which is the sum of limits. Same kind of thing. Okay, problem C. So what do we have and what do we want? And again, I always start with what we have and what we want, and then I unpackage them if I need to and try to find a path between them. So we have that the limit as n goes to infinity of xn equals x, and the limit as n goes to infinity of yn equals y. Those are what we're given. And what we want is that the limit as n goes to infinity of xn plus yn equals x plus y. Okay, and again, you're going to have to unpackage this. So in particular here for what we want, I think this is a situation where you really just want to do it in terms of the full epsilon n. So what we really want is we want to say, given any epsilon greater than 0, that xn plus yn minus x plus y, that's going to be less than epsilon. When is it going to be less than epsilon? It's going to say for all n greater than n, and what we're looking for, we must find n such that all this works. Let me. I think this arrow is confusing. Let me erase the arrow. Must find n such that this works. Why did I say given any epsilon must find n rather than saying for all epsilon there exists n? Of course, for all epsilon there exists n is the same as given any epsilon must find n, but by sort of changing the tense of these things, I think, put it into the framework that is going to be nice in our proof. The proof is going to start with given any epsilon, this thing, and we are going to show the reader of the proof how we can find the capital N. So it's very important that, like, when you're writing the proof, you're sort of imagining the reader as this person reading it, and that is really what is going on. And by very slightly changing it like this, I think it's a lot clearer to the reader. You can also, and I've seen this a few times, people sort of get mixed up between n is this thing and there exists n that is this thing. Of course, if I can find a particular n that works, there must exist one. But it's easy to get, when you say there exists n, to get mixed up in the sort of the generality of it and like the local scope of the variables and things like that. So I really like this way of phrasing it. And in fact, so my proof is going to start with given any epsilon greater than 0. Whenever you have to prove this kind of thing, it's a good idea to start with given any epsilon greater than 0. And then my job in the proof is to find the capital N that works. Okay, how am I going to find the capital N? Well, the things that I have are also these kinds of n epsilon things. But in this case, I really think of it as a for all. So I say for all epsilon greater than 0. And why is it a for all over here, but it's a given over here? Well, my job in the proof is using any given epsilon to find the n. But inside my proof, I'm going to use lots of different epsilons maybe. Maybe I'll plug in like 5 different epsilons into this thing. And so I really think of this limit as like a little factory. It's a factory. This is the limit as n goes to infinity of xn equals x. It's a factory that inputs any epsilon I want. I can chuck any epsilon in there, and what's going to come out on the other side is a capital N that makes the things within epsilon, right? So this one really is a for all, because I'm thinking in my head, this is a machine that converts epsilons into n's. I might want to feed in lots of different epsilons, and that's why I'm thinking about it that way. So for all epsilon greater than 0, to say there exists n, right? The n comes out of the factory such that norm of xn minus x is less than epsilon for n bigger than n. Okay, and I didn't leave myself enough room. So I have this machine that can make things within epsilon, and I have this machine that can make things within epsilon of y over here. That's another factory. And I have to use the machines to find capital N. So of course, the way the proof is going to go is I'm going to somehow feed something into this machine and this machine to get my n's. I'm going to have like an nx and an ny coming out of this one and that one. And then I'm going to combine those somehow to get the n that works over here. Like, that's the only possible thing that could happen in this proof. And, we did this one in class a little bit. You probably know by now the trick is to use an epsilon over 2. Let's pretend you didn't know the trick and you just did it with epsilon, and then we'll fix that up at the end. That's another good way to do it. So given any epsilon greater than 0, and here's the way you would write, I'm using the machine. You'd say since limit as n goes to infinity of xn equals x can find n, let's call it nx, such that the norm of x minus xn minus x is less than epsilon for n bigger than nx. Okay. Again, this is another situation. Some people would write, this is, misleading. It's like slightly wrong. Some people would write the following. They'd say, since limit as n goes to infinity xn equals x, and then they write the definition. They say, for all epsilon greater than 0 exists nx, ... Right? What you're telling me is that in general, there is an nx, but over here, I have actually defined a specific nx that I'm using in my proof. So if you write something like this, and then later on you say nx, blah, 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 like you've mixed things up, because the there exists nx is like saying, oh, I could find one, and here I've actually found one, and I'm saying take this one and call it nx. So this, this point in time is not the time to be writing for all there exists. This point in time is to be writing this specific epsilon naught, this specific nx. And if you mix these up, your proofs get slightly, less precise. So I'm saying this to say, don't do this thing. Let's leave it, but I'll cross it out in big red letters. Don't do this here, right? Of course, that is the definition, but we're invoking the definition at an exact spot. And that's the difference between the general and the specific invocation. Okay. All right. Same thing with y. Okay. Since, oh, now I have a thicker marker for some reason. Okay. Sure. Fine. We'll stick with the thicker marker. N goes to infinity of yn equals y, can find ny such that the norm of yn minus y is less than epsilon for n bigger than ny. Okay. All right, great. Now I'm going to combine these. How am I going to combine them? It's going to be the same triangle inequality stuff we did before. So what I would like, going to the what I want, I would like this thing to be less than epsilon. So let's write my sequence of chain of inequalities. So I say now consider, and I'm going to have a chain of inequalities that starts at x plus y, or xn plus yn minus x plus y, and it's going to end, it better end at less than epsilon, right? Because that's what I want. And what could it possibly be? What's going to be triangle inequality? Okay, so xn minus x plus yn minus y. Okay, and this is a less than or equal to, and I can say by triangle inequality, by triangle iniq. Okay, and again, I'm using the form of triangle inequality that says you have the norm of something plus something else. It's less than the norm of the first something plus the norm of the second something. Very good. And then now is where you got to be careful. So some people will write less than epsilon plus epsilon, and you could even say you could give these things names. That's a good habit. Let's give these things some names. Let's call this star x, and this is star y. So you can say by star x and star y, by star x and star y. Okay, but if you do that, you have actually missed something. And the reason is, remember, star x and star y, they only hold when n is bigger than ny and n is bigger than nx. Okay, they don't hold for every single n. And this is another thing people have been missing, is talking about the qualifiers on the n's. So the n's, you need to make sure you talk about for which n is this true. And so what I'm going to say here is star x and star y, and then I'll write because n is bigger than nx and n is bigger than ny. So if I include that, then it's correct. Why is it true that n should be bigger than nx and bigger than ny? I need to somehow explain why this is true. And I left a little bit of space right here to do that. And this is the choice of n. So I'm going to say set capital N to be the maximum of nx and ny. And I'm going to say so that n bigger than n means n is bigger than nx and n is bigger than ny. And that's going to let me apply star x and star y. So this is a detail that some people have been missing, and it's an important detail that comes up a lot. Of course, you can see like why I'm using it, right? It's like I want to be able to use it for both, and I'm setting up a situation where the n's are such that I can use both star x and star y. Okay, very nice. Okay, you might notice again, just like last proof, it doesn't work out with an epsilon, it works out with a 2 epsilon. I think the easiest way to fix it in this case is to go back and just replace things with epsilon over 2, because remember, the epsilon factories can feed in any epsilon. So I can just put an over 2 here, and it's all good. And everything is still true. Since the limit is x, right, I can feed in any epsilon I want. I fed in epsilon over 2. Okay, so now that is a nice worked out proof of that thing. Okay, what else to say about this one? It's extremely similar to the one in R. This one you should know cold. It has all the good details about epsilon over 2 arguments, and also triangle inequality, and like setting things up is a very good habit to get into. Okay, so given any epsilon over 2, this epsilon, let's do one last line and say, since this holds for any epsilon, or maybe even better, I could say, since we found such an n for any epsilon, then the limit as n goes to infinity of xn plus yn equals x plus y as desired. Just to round things off and make sure the reader knows like, hey, we're done here. Why are we done? The reason we're done is because we found the n that worked for no matter what epsilon you gave me. Okay, that seals things off for question 22C. Now we're ready for question 1 from the Tuesday's other thing, proving that f is a norm. This one is a little bit different in that the things you're given are slightly different. So prove the infinity norm, some people write it like this, is a norm. So this little dot is standing in for unnamed function, right? So I'm not saying the norm of the function f, I'm saying the norm object, the thing that does the norm, is a norm. And remember the norm, this infinity norm, I'm not going to write infinities because it's the only norm we're working with right now. The norm of f is the maximum of x in 0, 1 of the absolute value of f of x. Okay, there we go. Okay, how are we going to prove it's a norm? I'm going to do the 3 properties from the textbook, and the first property says that the norm of f equals 0 implies the f is the 0 function. So is the 0 vector, which in our particular case means f of x equals 0 for all x in 0, 1. That's what we're trying to show. Okay, what do we have? What do we want? Okay, this is what we want. This is good. I've already unpackaged one layer. This is what we want. What do we have? We have that this is true. The norm is 0. So again, I'm sort of thinking of have, want, and the ideas phase. The norm of f being 0 means the maximum of x in 0, 1 of the absolute value of f of x equals 0. So if the maximum is of the absolute values is 0, why would it be true that every individual value is 0? And this is in your proof. You have to very clearly, delineate every individual value versus the maximum and be careful about that. In this particular case, it's not so bad because you say, what do we want? We want something for all x. So we could say for any, here's the proof, for any given x in 0, 1, right? So I'm doing for all by starting with given any x. F of x, well, f of x is actually less than or equal to the absolute value of f of x. Or actually, why don't I do this? It's 0 if and only if the absolute value is 0. So f of x equals 0 if and only if the absolute value of f of x is equal to 0, right? So it suffices to show that the absolute value of f of x equals 0. And again, remember, because I said given any x bigger than in 0, 1 at the beginning, now I can treat x as some fixed value. It's not some anonymous value. I don't have to be careful about which x's I'm talking about. I'm talking about this particular x that was given to me at the beginning of my proof. Okay, so we want to show that the absolute value of f of x equals 0. But notice 0 is less than or equal to the absolute value of f of x because absolute values are always non-negative. And that is less than the maximum over all the possible f's. Here, I better use a letter other than x, right? X has been reserved over here. Actually, why don't I make this one, a particular instantiation? Why don't I call it x naught? And then I can do the maximum over all x in 0, 1 of f of x, right? So a particular value is definitely less than all the values, which is 0 by hypothesis, right? Given by norm of f equals 0 given. So we were given that this is 0. And now I have a sandwich. 0 is less than something, ... equals 0. Therefore, by the inequality sandwich, absolute value of f of x naught equals 0. It must be 0. It's somewhere between 0 and 0, so it has to be 0. Since this holds for all x naught, therefore f of x equals 0 for all. Okay, let's leave it as a. Okay, I want to leave it as, let's call this one x. See, I really want to try hard to not mix up, like when I'm saying a qualifier, like something's true for all x with the particular ones, like x naught. So why don't I leave this one as x? F of x equals 0 for all x in 0, 1. Okay, very nice. That is part A, which is if the norm is 0. Okay, and actually I should write this as a little claim. Norm of f equals 0 implies f equals 0 as the 0 function. So here I've like delineated what I'm doing. All of this stuff this was ideas phase. Okay, so when you hand it in, the ideas phase maybe doesn't even need to be on your final answer, right? It's just the proof needs to be on the end. Okay, very good. That's the first part. Part B of being a norm is that it's scalar multiplication, and this one I think is actually quite quick. So let's say claim. It's always nice to say when you have a statement in math, you always got to put the statement in context. if your statement is something you're claiming is true, then write claim next to it. If your statement is something you're going to say this is false, then write, we will see that this is false or something, right? Okay, so claim is that for all f in C01 and lambda in R, that the norm of lambda f equals absolute value of lambda times the norm of f. And this one is essentially almost just like a straight calculation. You start on the left-hand side with lambda f, which is the maximum of all x in 0, 1 of lambda times f of x. Okay, and here's the secret sauce. You can pull it out like this, and you should justify why with 1 or 2 words, the maximum like this. And I think you could say, why is it that you do the maximum of lambda times f? Ooh, you know what you could do? Let's do one more line. Let's put this one in between. And then this one is like totally uncontroversial, right? I'm just pulling out the absolute value. And then I can do one more line where I pull out the lambda. And okay, and I say it's okay to pull it out because absolute value of lambda scales all x values in the same way. So we're multiplying every single x value by the same absolute value of lambda. So where the maximum is, that will not change. That'll be the same. Okay, very nice. Okay, and last but not least, this is lambda times the norm of f. So this thing is the norm of f. So this one really is the only, you can do this chain of equal signs and you just need a one little justification over here. Okay, last but not least, we got triangle inequality. And triangle inequality says, claim the norm of f plus g is less than the norm of f plus the norm of g. Very nice. Okay, and again, I'm going to start with a chain of equalities. And if you have a chain of inequalities and you've decorated it with the right explanations for the right lines, that is a perfectly good, clear proof. So the norm of f plus g is the maximum of x in 0, 1 of f of x plus g of x. Okay. And then you could say this is less than or equal to the maximum in x in 0, 1 of f of x plus g of x with absolute values like this. And then you could say by the triangle inequality on R, where the ordinary triangle inequality for absolute value means that you can do this over here. And now here is the part I think some people were struggling to justify. So I think lots of people saw this. And I think the way I would do it is I would give these things a name. So it's true, you can write it totally like this. But to me, the thing that is really the difference between this line and the line after it is here we have a variable x for the f's, here we have a variable x for the g's, but they can be different variables. So why don't we call this one x f and this one xg? And really what's going on here is we're saying you can choose any xf and xg you want. And up here, where we had just one x, they had to be exactly the same thing. So the reason the maximum gets larger is you could say we have the flexibility to choose, on the right-hand side, we have the flexibility to choose xf not equal to xg. So the maximum over x is less than or equal to the maximum over xf dot 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 plus the maximum of xg dot dot dot. So this is kind of taking the idea that I just said out loud, is that we have more flexibility, and so the maximum can only get larger. Very specifically, like you could do it with subsets. You could say like the set of all x where xf equals xg is a subset of all of them, this kind of thing. But I think this kind of little short sentence description is the perfect level of detail that we want. Okay, and then this is equal to the norm of f plus the norm of g, which is what we wanted. Okay, very nice. Okay, so those three together, you could maybe add a line that says those are the three axioms of the norm, and therefore it works. It's a perfectly nice solution. Okay, last but not least here, let's do the last problem, which is pointwise and norm convergence are the same in RD. This is really two proofs. If it converges pointwise, then it converges in norm in RD, and the reverse. One direction is very easy. Let's do this direction first. if xn converges to x in norm, so in the infinity norm, then xn goes to x pointwise. Okay, and this is a good situation. What do we have? What do we want? We have that the convergence in norm. So the limit as n goes to infinity of xn equals x in norm. And what do we want? We want convergence pointwise. So we want for all I, all the indices I in 1 to d. Oh, did I call them v's? Let's call them v's so we don't get... I'm going to call them x's here because the proof we're about to do actually works in any space. So you'll see that works in any space. So let's just call them x's instead of v's. Okay, now I feel bad though because it says v in the problem. Okay, you have convinced me. Congratulations. I will change it to v instead of x. Okay, let's change it to v instead of x, and then I won't explicitly say that it always works. You'll just have to use your brain and imagine why it works even in other spaces. Okay, vn goes to v. Vn goes to v in norm. Then vn goes to v pointwise. Let's fix the notation. Vn equals v in norm. So for all I in 1 to d, vn of I equals vi, the limit. Okay, so actually, again, the thing we want is a for all. So in my proof, absolutely, I don't even know what I'm going to do yet. And the proof is going to start with given any I, given any I in 1 to d, and then we're going to work this out, and we're going to have to prove that the limit is this much. And again, you have what you have, you have what you want. What you have and what you want will always have several definitions in them, and you can unpackage more or less to sort of like see what's going on. And in this particular case, I think it's worth it to write down what the norm convergence means. It means that the norm of vn minus v is less than epsilon eventually. And over here, for all epsilon, this is eventually. And then again, this is ideas. In ideas land, I don't have to be precise. I don't have to write for all. I don't have to write there exists and all that. I just have that in my head, in my ideas, and that's included in the word eventually. And then I kind of imagine that, and then when I translate it into my proof, I'll have to take eventually and convert it into there exists and blah, blah, blah. Okay, so vn minus v is less than epsilon eventually. And what I want to show is I want to show for all epsilon that absolute value of vn of I minus vi is less than epsilon, right? So some particular entry is less than epsilon. But vn minus v is the maximum over all the I of vn minus v. I is less than epsilon. So what I have is that the maximum is less than epsilon, and what I want is that one particular one is less than epsilon. And again, just like before, any individual one is going to be less than the maximum. So it's all going to be good. We're going to have a chain of inequalities. This thing is going to be less than the maximum, which is less than epsilon. So this is my connection. By unpackaging it this much, I can see how what I want really comes directly from what I have. I have that the maximum is less than epsilon, so any individual one is going to be less than epsilon. The hardest part is just organizing the proof with like the givens and the for alls and the converting the eventuallys and so on. But let's do it carefully. So we're given any I, and it's nice to say what we want to show. We want to show the limit. The limit as n goes to infinity of vn of I equals v of I. Okay, this is an honest to God limit in R, right? This is like first year calculus 2 or whatever, where you learn sequences. Sequence of numbers converging to another sequence of numbers. Okay, and then I'm going to have to get to epsilons. So to see this, given any epsilon greater than 0, right? Because every time you prove a limit with an epsilon, you need to say given any epsilon greater than 0. So now I've been given an I, and I want to show the limit. And to show the limit, I need to be given an epsilon. And I'm going to say, okay, maybe I can scroll down a bit, and then I know my proof is going to go like this. It's going to say vn of I minus vi, and it's going to end with less than epsilon. Okay, and the thing in between, this is going to be less than or equal to the maximum over all the i's. And again, okay, maybe I should use a specific notation. Let's call this I0 so that we know that this is the specific I we're talking about. So the specific instantiation of the I will be I0, and then I can save the variable I, the letter, to be my anonymous variable in the maximum I 1 to d of v of vn of I minus v of I. Okay, so here's the secret sauce that we're going to use. The particular entry we're talking about, vn of I, is less than the maximum over all the entries, and that's going to be less than epsilon. Right? That was what our idea was. How am I going to write this down? I got to choose it so that this works. So I'm going to say since the limit as n goes to infinity of vn equals v in norm, that was the thing that was given to us. Therefore, the norm of vn minus v is less than epsilon. And this is where I can't write eventually because I'm in the actual proof. I have to write, therefore, there exists. Let me not write there exists. There is some, right? Because there exists is like, oh, there's some anonymous guy. But I want to give it a name, and I want to use the name here. So there is n, some natural number, so that vn minus v is less than epsilon when n is bigger than n. Okay. So this is written with the norm. This one is written without the norm. I think I can insert the norm by just adding one more line. This thing equals the norm. This thing equals the norm of vn minus v. The maximum is the norm, and then this is less than epsilon. And so now I can say by star choice of n. So this is star, equation star. So star. Okay. Okay, it would be nicer if I wrote it on its own line so that it really could be a nice star, but let's go with that for now. Okay. Vn of I minus vi is less than vn minus v is less than epsilon. Okay, wonderful. Okay, the only thing I haven't justified is why this inequality is true, and then you could say maybe it's overkill to do this because I naught is in 1 to d, right? I naught is one of these guys, so it's less than the maximum. Okay, so vn of I naught minus vi is less than epsilon, and then that's it. We've done the whole thing. Okay, maybe to wrap it up, you say since epsilon is arbitrary, the limit as n goes to infinity of vn of I naught equals v of I naught, and then you say since I naught is arbitrary, we have pointwise convergence. Okay, beautiful. The proof we just did actually also works even in spaces that are larger than 1 to d. So if you replace the set 1 to d in this little box here with the interval 0, 1, the proof is the same. If you have norm convergence, you will also always have pointwise convergence. So if things converge in norm, then they converge pointwise. That's always a true statement. The reverse that we're about to do, so let's do the reverse direction. If vn to v pointwise, so let's say vn is in r to the d, some sequence in r to the d, and vn goes to v pointwise, then vn goes to v in norm. This statement is only true in finite dimensional spaces. So in infinite dimensional spaces, this will be false, and we'll see lots of counterexamples. That'll be the fun of the course. But in RD, if you converge pointwise, then you converge in norm. And again, let's, instead of jumping right into the proof, let's think about what we have and what we want. So what we want is that the limit as n goes to infinity of vn equals v in norm, the norm limit. And what we have is the pointwise limit. The pointwise limit, I'm just going to write it out like this. We have that for all I in 1 to d, vn of I, the limit of the vn's equals v of I. And now you got to start unpacking, right? So this thing over here is a limit of honest numbers, but this thing is a limit of vectors. And what did we do for a limit of vectors in norm? Well, that means really that for all epsilon, the norm of vn minus v is less than epsilon eventually. Okay, and the eventually you're going to see is that's really doing the heavy lifting here. So what does it mean eventually? It means that the maximum over all the i's of vn of I minus vi is less than epsilon eventually. Okay, so we need the maximum to be less than epsilon eventually. I think this is the line where you need to use to have the right way of thinking about it. And this is the secret. The maximum is less than epsilon. That has to eventually happen for a large enough n. The maximum being less than epsilon means every single entry is less than epsilon. So we're using this property that the maximum of a bunch of numbers, the maximum, I don't know, let's call them R for number, R for real number. So the maximum over some set, you have a bunch of real numbers. The maximum is less than something. Let's call this something B for bound. If and only if RA is less than B for all A and A. The maximum can be less than something only when every individual number is less than the thing. And the reverse is true too. If every individual thing is less than B, then the maximum will be less than B too. So this is, I think, the level of unpacking that really helps you out. And because it gets rid of the maximum, right? It replaces the maximum with a for all, and that's the kind of thing we have up there. So the maximum being less than epsilon eventually, that means that every individual one, say for all I, eventually. Okay, and this is why we're in ideas land, and you got to be a little bit careful sometimes with your eventuallys. So what this means is eventually there is some point where this is true for every single I. So we need this to simultaneously be true for all I simultaneously at the exact same time. So that is a detail that can trip you up because what I've written looks like the pointwise convergence. Pointwise convergence says for all I, these things are all eventually less than epsilon. And this convergence says eventually all of them are less than epsilon. And those look the same, but they're very subtly different because it's the simultaneously thing, right? For the norm, they need to all be less than epsilon. At the same time, there needs to be one capital N that works for all of them. In this situation, we have one for every individual I. So if I unpack this limit, this means that Vn of I, so this says for all I going from 1 to d, Vn of I minus V of I is less than epsilon eventually. And what I want is that I want it to be true for all the i's eventually. And I have that for every given I, it's eventually true. And I want to find one particular thing that makes that all work. And now is the time where, if you're confused by this, if you're not seeing where I'm going, you need to actually turn these eventuallys into n's. So for all I, there exists ni such that that's what eventually means, right? Okay, that's what we have. So we have for every I, there's an ni. And what we want is there's one single n so that this works for all the i's. So we want, okay, let me see, what did I write up here? So we know that for all I there exists an ni, and we want to find, want n such that this thing is true for all I when n is bigger than n. Okay, so for all I in 1 to d. Okay, so that's the difference. We have an ni for every individual I, and what we want is an n that works for all the i's at the same time. Okay, how are we going to do this? Well, in this particular case, there is a trick. We used it earlier, which is you just take the maximum. So the idea, this is the big idea, is just let n equal the maximum of n1 dot nd, right? And by doing the maximum of all these things, there's d of them. It's totally legit to do the maximum. Just take the biggest one. And if n is bigger than capital N, then it'll be bigger than all the other n1, n2, n3, and so on. And then we will know that this works for every single one. That is the trick. And I've kind of tried to show you how to get it by unpackaging what you have and what you want, and then seeing like how they're similar and how they're different, and then leading to this idea of the maximum. Okay, that's all ideas land. Let's actually prove it now. Okay, let's prove it. Okay, so the proof, again, leads you from what you have to what you want. What we want is this thing. We want this limit. We're going to start, any good proof starts with given any epsilon greater than 0. Okay, and we're going to try to prove why this thing is less than epsilon. Okay, we must want to find. Okay, you don't need to write this want to find thing, but if the proof gets complicated, sometimes you get confused, so it's nice to write want to find n such that the norm of Vn minus V is less than epsilon whenever we want to find whenever n is bigger than n. Okay. Okay, let's do it. So what is the proof? Okay, since we're going to use the thing we said we'd use this, okay? So since Vn goes to V pointwise, we know limit, well, let's say for all I in 1 to d, for all I in 1 to d, limit as n goes to infinity of Vn of I equals Vi. Okay, and if the limit of Vn of I equals Vi, I'll say hence we can find on Ni such that Vn of I minus V of I is less than epsilon for all n bigger than Ni. Okay, and this is a nice equation. Let's call this equation star sub I. Star sub I. So this is true for all I, and so for every individual I, we want this. You know what? Actually, I'm not happy with the way I wrote this. I said we know for all I, blah, 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 and then I'm using the i's as actual variables. If you say for all I, it's kind of like I want to keep I anonymously. So I think it's better to say for any I instead of the for all, right? Because so we know for any, and I can even say for any fixed. So in this line of argument, I is some fixed variable. So for any fixed I, this limit equals Vi, and so we can find an Ni such that this holds. Okay, here we go. We've set up this thing. We've got the Ni's, this holds, and now I'm doing the idea that I had, which is to take the maximum, and when I take the maximum, this will be true, and then I will write out what this is and explain why that is the thing we wanted. Okay, that'll be the proof. Okay, so now consider n, which is the maximum over all the i's. Or maybe I could say do this for every I. For every I in the set we're talking about. The maximum over all the ni's. So n is the maximum of all the ni's. And then I'll even remind the reader why we're doing this maximum trick in the first place. Notice if n is bigger than n, then n is bigger than ni, so star I holds. So this is telling the reader, look, the reason I'm taking the maximum is so that I have every single condition star I holding at the same time as long as n is bigger than n. Okay, very nice. Hence, for n bigger than ni, so n is bigger than n, we have so we have Vn of I minus V of I that is less than epsilon, and this holds for all the i's now, for all I in 1 to d, right? Right, this is because star I just told them star I holds for all I, holds for all I, let's add. Vn of I minus Vi is less than epsilon for all I going from 1 to d, and therefore, this is the key, if it holds for every single one, the maximum is also less than epsilon. Vn of I minus V of I is less than epsilon. If every single thing is less than epsilon, then the maximum over all the things, that must also be less than epsilon. And that equals the norm of Vn minus V by definition. So if the maximum is less than epsilon, the norm is less than epsilon. Okay, and then this is what we wanted to show. So finally I say since epsilon is arbitrary, this shows the limit as n goes to infinity of Vn equals V in norm. Okay, and that's the proof. Hopefully this going kind of like roundabout and talking about my ideas and what I have and what I want, that was actually helpful to you. Of course, you don't have to do all that, right? Like the only thing you hand in at the end is the proof, but maybe this will help you see how I came up with the proof and like what are the important parts of how you take your ideas and convert them into a nice proof.